Okay, so thank you very much. So first, I'd like to thank organizers for giving me the chance to be here. This very cozy place and very fascinating meeting. So I'm Jun-Ichiro from Japan, and mainly belonging to the Open University of Japan and also University of Tokyo and the Institute of Molecular Science. Today, I will talk about electron-chiral phonon coupling and the related topics. And this is my collaborators, all belonging to also Quantum Research Chirality Research Center for Institute of Molecular Science. And in my understanding, the perspective of this meeting may change depending on whether the emphasis is placed on chiral or phonon. So chiral phonon or chiral phonon, like that. Yeah. And clearly, I am rather on this side. So we have long studied chirality-related phenomena because chirality selective cross-coupling is very robust and very interesting and very ubiquitous. So the chirality selective cross-coupling just means handshake. Yeah. And your left hand and another person the same handedness can shake hands, right? So the chiral materials, so the chirality selective cross-coupling causes very abundant cross-coupling, like among magnetism and electricity and elasticity. So this cross-coupling produces quite abundant, quite a lot of topics. Okay, and today I will talk about first the motivation about how we put emphasis on chirality selective coupling, but I will go very quickly about this point. And second, I will talk about chiral phonon, especially I emphasize the importance of crystal angular momentum and phonon chirality. This issue is repeatedly mentioned already today. And finally, I will tell you about how to describe electron and chiral phonon interaction in a naive manner, so based on the lattice model. Yeah, and today's my talk is mainly based on these references and the people written in red sitting here, so getting together here in this room. Yeah, Togawa-san and Tian-san and Murakami Shuichi-san and Sato-san. And okay, and first, okay, so. Now, I always begin with our definition of true chiral phonon. Is chiral phonons are a quantum of lattice vibration, the way the rotational motion of atomic nuclei propagate out of wave with a finite, non-zero wave number in the direction of rotational axis. So this is the nothing more than a coupling between the rotation and the translation. So rotation means angular momentum. This is the actual vector. And translation means the wave number. This is the polar vector. It's a dot product. It's nothing more than simply gives the time even pseudoscalar, or sometimes we call this electric toroidal monopole in terms of multiple language. Yeah. So we stress this point in these two references. And we stress this point in the paper together with Sato-san and Togawa-san and Murakami-san in this paper. So this is paper, the experimental paper. Yeah, so already Sato-san made a detailed report already today. Okay, so again, so I very quickly go through the meaning. So chirality selective coupling between two chiral dual entities. This is nothing more than just the relation between the bolt and the nut. Yeah, so left-handed bolt and right-handed, left and right. This is right. Yeah, right. this is favored. Yeah, this is favored. Yes, right. Sorry. Left and right. This favored, but right and right are favored, of course. Yeah, this is shake hand. The shaking hand. So the chirality selective coupling is quite robust, like you shaking hand, like that. Okay. So the in chiral, how to say, in materials, the food shake hands is the one guy is chiral wave, like phonon, electron, or photon, and magnon. And once quantized, it becomes quasi-particle, yes, phonon, electron, photon. and like that. And another mate, dual mate, is chiral materials, like chiral molecule, chiral crystal, chiral elastic body, and even metamaterials. So these chirality, first chirality and the second chirality meet each other and shake hands. This is the chirality selective coupling, and their selectivity is very robust. So and dual, and the main scope of our research is that how to describe this from a physics viewpoint, and I'm a theorist, so it's not so easy to have a general view, but step by step we elaborating on the approach in this grand view. Okay, and so this is the second point, and chiral phonon. So I think this is the main topics of this meeting. So the important point in the here I stress that having stereosymmetry is a narrower concept than being chiral. Yeah, so being chirality does not always mean the stereosymmetry existence. So of course, yeah, just C1 symmetry is nothing. But no symmetry, no way for physicists almost. Yeah. So the having stereosymmetry is a narrower concept than being chiral, but it leads to a conserved angular momentum associated with the corresponding discrete rotational symmetry like this. Yeah. So as an example, so let's consider a threefold screw as an example. So in this case, so of course, this is inside a crystal, so continuous rotational symmetry is broken. So this means that the mechanical angular momentum, U cross U dot type usual mechanical angular momentum is not conserved. However, but because of the thanks to the discrete threefold 2 power over 3 rotational symmetry, so crystal angular momentum, it conserves here. This is called crystal angular momentum, or quite often called also pseudo angular momentum, as the Professor Tan introduced this morning. Okay, so now I will focus on this case as a model. Okay, so now, so of course, the many works have been done from a numerical viewpoint over the half century. But now, so I needed to write an analytical closed formula for chiral phonon. So we did do that. So how to describe wave function of chiral phonon? So phonon is, of course, a vectorial field. Vector field is a bit more complicated than electron. Yeah. So not a scalar, but a vector. So because of that, so a bit the appearance is a bit complicated. So this detailed information was presented in this paper, recent paper. But this formula is nothing more than just a Bloch theorem in the case of usual crystal. However, in the case of the stereosymmetric crystal, in addition to the crystal momentum, or wave number, in addition to the wave number, we have another level to diagonalize the dynamical degrees of freedom. This is nothing more than a CAM, crystal angular momentum or pseudo angular momentum. Yeah. And in addition to that, besides, also because of the superposition of bases is also required, because the phonon displacement is x, y, and z, three-dimensional. So we need to make a superposition of three orthogonal bases. So because of that, the appearance is a bit complicated, but the physical meaning is quite simple. This is just a generalized Bloch theorem in the case of stereosymmetric crystal. Yeah. So the Qn is crystal momentum, M is crystal angular momentum, L is the site number in real space. Okay. Now, so by taking advantage of this symmetry, like in a more specific way, like representation theory, group representation theory, we can quite easily diagonalize the dynamical matrix, and we have a closed formula for the dispersion of the chiral phonon, which propagate along the screw axis like this. So by using it, for example, just mathematics, so we can quickly draw these phonon dispersion just by inputting crystal parameter like this. So I think so this dispersion is quite well known in this community. And the crystal angular momentum is the level which specify that each branch of dispersion and m equal to 0 correspond to the longitudinal mode, and m equal to +1 and -1 correspond to the, usually we call them the transverse mode. Yeah. However, so in the case of the screw symmetric crystals, it's quite, how to say, unusual that the longitudinal and the transverse modes, the distinction among them does not make any sense, because transverse mode mixed up with the longitudinal and vice versa for a non-zero wave number. Yeah. So this point was, of course, already pointed out. For example, Murakami-san's paper in early 2018, like this, based on a numerical computation. But now we can give the the explicit wave function in real space, and we can freely draw the like real space trajectories of nuclei in each position. For example, on the dispersion B, C, D, and E, F, G correspond to B, C, D, E, F, G. This view graph is a bit messy, but what's important is that there is no clear longitudinal or transverse mode. Yeah, so this is a seemingly like apparently longitudinal at the B point, apparently, but however it's bent, not purely longitudinal, but a bit horizontal component there. And as we travel from gamma point to the Brillouin on H, so these orbital plane can't. And finally, for example, in the case of acoustic branch, so the longitudinal mode is purely longitudinal near the gamma point, but this green longitudinal trajectory totally becomes horizontal near the zone boundary. Yeah, and of course, this is already known. However, but now we can show this in a more explicit manner. So now it's an important point is the longitudinal or transverse mode are mixed up. So this means that usually if you open the textbook, so electron can couple with only longitudinal phonon mode. However, now, how to say, transverse mode can also come up in electron-phonon interaction. This means that the chiral nature of phonon, so left-handed or right-handedness, can come up in electron-phonon interaction. This is quite an important point. This peculiar nature of the chiral phonon. Yeah. So otherwise, so how to say, the chiral phonon is just, if we are sticking to an idea that the chiral phonon is just transverse, there is no chance for electron to couple with them. However, in the case of truly chiral phonon, it's possible for electron to couple with the chiral phonon, actually. Now, of course, we can repeat the same analysis already done by Chan and New more than 10 years ago, and we can input the explicit form of the wave function and a little bit modified form of the angular momentum. And what's a bit new is that just so coherence factor appears. So and now so we can easily draw the momentum dependence of the Q dependence of MAM. MAM is a mechanical angular momentum for acoustic branch, optical branch, and second optical branch. Yeah, we have two optical branches like this. So it's clearly seen that the mechanical angular momentum very sensibly depend on Q, so it never be conserved. Yeah, never be conserved. Of course, maybe almost everyone knows this fact, but we can see explicit manner that the mechanical momentum is like this. However, the sign of angular momentum is strongly correlated with M, conserved crystal angular momentum. Yeah, like this. So M equal to -1, 0, +1 is very strongly correlated, how to say, almost fix the sign of the angular momentum, direction, orientation. So this means that through the conserved crystal angular momentum, we can control mechanical angular momentum, yes, because conserved angular momentum is very strong. Yeah, so they can be useful to control the mechanical angular momentum. And this is also the case for optical mode like this. And another maybe a bit seemingly interesting quantity is quantity analogous to Rifkin's optical zilch. So this is this quantity was discovered in 1964 by Rifkin, and this is the equation for the electromagnetic field for traveling electromagnetic wave. So E is of course electric field associated with electromagnetic wave, and B is magnetic field. Yeah, and Rifkin discovered that this combination is completely conserved in the vacuum. So of course, if there is inside the material, charge density and charge current exists, and then so the conservation law is broken. But in the case in a vacuum, this is totally conserved. And however, at the time, the meaning of this strange combination was not so clear. But how to say? So in about 10 years ago, sorry, I missed the reference, but Tang and Cohen. So notice that this is nothing more than the time-even pseudoscalar and the measure of chirality, and this and ratio of this is a bit, how to say, a bit of the generalization of energy density of electromagnetic wave. However, the spatial structure enters here, and some ratio of this one and the energy density divided by energy density gives you the anisotropy of CD. Yeah, so circular dichroisms. So because of that, so after the Tang Cohen's paper, this quantity became revived, and now it's quite, how to say, a target of very active research. So now, so it's a bit interesting to construct analogous quantity like this, U dot rotation, a curl of U like this. So of course, we have an explicit formula for the wave function, and we can easily calculate, and some interference factor appears, and we can compute the phonon zilch. But unfortunately, in the case of phonon, so of course, phonon occurs inside the material, so Z is not a conserved quantity. However, there is strong correlation between the mechanical angular momentum and the zilch, like this. So I hope that the zilch is, how to say, a non-local, carries non-local information about chirality. So like zilch interaction may give you some chirality selective coupling, so blah, blah. So now I hope that this is a kind of starting point to elaborate on understanding of the chirality selective interaction. And finally, I talk about how to describe electron and chiral phonon interaction. As I mentioned, in the chiral Scurio crystal, so electron and phonon can couple, and chiral phonon can come up in interaction. So in the case of phonon, as a phonon operator, I already gave the formula. So in the previous slide, and like this. And of course, the similar expression for electron annihilation operator like this. And of course, electron also hops on the helix. Yeah, so the symmetry is the same. They feel the symmetry, the same symmetry. Phonon and electron feel exactly the same symmetry environment. So like the label here, so for diagonalization, so wave number and crystal angular momentum also appear in the electron. And I want to point out that the difference of the crystal angular momentum or pseudo angular momentum for the electron in the propagating in the Scurio crystal was already pointed out by Bozovich in 1984. He clearly wrote down this formula. But how to say, he just, like that, okay. And how to describe the electron-phonon interaction? It's quite straightforward. And by starting with the tidal binding Hamiltonian, and we expand this hopping integral around the stationary position like this, so then the U is like this. So now we take account, or how to say, we need to do some approximation how this gradient of the hopping integral is described. And now, so we followed the idea by Friedel like this, and Friedel, and this is quite understandable assumption that the gradient is just point in the direction of this directing bond. Yeah, so this green line. So this green line is corresponding to the direction of this gradient. So once we take account of this approximation, it's quite easy to go ahead, and we can straightforwardly write down the electron-phonon interaction. And of course, so the electron-phonon interaction coupling balances depend on not only N means wave number, and M means crystal angular momentum or pseudo angular momentum. So this coupling depends on both N and M. So this is a bit different from usual electron-phonon interaction in textbook like this. So this is a bit technical, but we can directly derive the electron-phonon barracks for the case of 3-fold screw symmetry. And by using this, we can go ahead. So once we get interaction barracks, we can basically compute many quantum processes by using perturbation theory. And it's to be noted that this interaction barracks satisfy the time reversal symmetry. This is, of course, because there is no source of time symmetry breaking in this case. So this time reversal symmetry is preserved. And also, it is to be noted that if we take the limit of rho, rho is the radius of helix. Yeah, so if we take the limit of rho approaching 0, we exactly reproduce the result of Friedel like this. So this is a result from Friedel's paper. So this result is totally reproduced by taking a limit of rho equals 0. So this interaction barracks is like a general or extension of the Friedel barracks to the case of screw symmetric crystal. Okay, so by using these barracks, for example, as an example, how to use this, so the Stokes-Raman and anti-Stokes-Raman quantum process can be expressed written down, and like this. So I don't get into detail, but anyway, so this Feynman diagram correctly explained the Sato-san, the Raman scattering experiment, and quantum description of experimental findings are now, how to say, are done by using this barracks. And also, I want to mention that maybe Ueda-san will sitting here and we'll talk about X-rays. And I adopted this Feynman diagram from Mars papers in 1994. This is a resonant inelastic X-ray scattering process. So by applying these electron-phonon interaction barracks, we can also explicitly describe X-ray processes. So I haven't done as yet, but it's how to say some like the promising to make a collaboration with experiment. And finally, so we briefly mentioned that sometimes the continuum field theory is quite useful. So far, I have mentioned lattice theory. However, by taking a continuum limit, we can get the so-called continuum limit near gamma point. So, of course, this theory is restricted to the near gamma point, but quite macroscopic. So whenever we want to discuss the macroscopic response, so electromagnetic response, like elastic response, and blah, 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 so the continuum theory is very useful, and rather simple, like Landau theory, exactly the similar philosophy, Landau theory. And however, so how to take a continuum limit from chiral lattice vibration is not so trivial. And we need to take account of so-called micropolar elasticity theory, which take account of not only translation, but rotational degrees of freedom of building blocks of chiral matter. So usually in the elasticity theory, we crush the lattice to the point, but if we crushing everything to the point, the chirality disappears. So we need to retain some chiral objects like this. So then this is like a rigid body rotation appears. So not only translation, but this appears here like this. This case, so we find that the so-called like Roton like dispersion appears due to the hybridization of translation rotation mode. And surprisingly, this Roton mode was recently really realized in the chiral metamaterials by the Karlsruhe group of the Wegener's group. Realized this Roton mode, theoretically predicted Roton mode in chiral metamaterials. Okay, so I summarize my talk, and this is the summary and outlook from chiral lattice vibration, the broader phenomena. So starting with chiral lattice vibration, once we quantize chiral phonon, electron, blah, 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 and blah, blah, blah. And, once we see, discuss based on the classical elasticity, chiral elastic wave appears, and the chiral metamaterials enters here. And my ultimate goal is to understand the Schiff phenomena. It's a very challenging phenomenon. So maybe Yoshi and Ron Darman and Yoshi Parotiero will tell us about the detail. However, it's a bit far. Not so far, but yeah. So every year I say that dawn is near, but still like a bit night too. However, yeah. Anyway, so now we accumulate necessary information from both microscopic and macroscopic viewpoint, or like this. So, and finally, so I say that how to control chirality selective cross-coupling based on chiralization, as Professor Sparoli mentioned, is quite important. So how to quantify the strength of dynamic coupling between two chiralities, very, very, yeah. So it's not so trivial matter. So, okay, so thank you for your attention.